Hello everyone, thank you for watching the video. Please do not forget to like the video and subscribe to my channel. By this episode, I would like to finalize the introduction to supervised learning by talking about the assumptions about the data. Let's discuss what is assumptions about the data and why do we care in the machine learning task. If we don't have any assumptions about the data set, we will get infinitely many solutions. It is illustrated by this example. Let's consider on this plot, I have several blue points in my training data, and each of these lines are a solution to my data set. And all of them can minimize the loss function to 0 because all these lines are passing exactly from this training data. Each data has a particular X and a particular Y. But the problem comes when we see the characteristic between two independent data points, because this makes the problem more complicated if we don't have any assumption. Which of these lines are a perfect fit for my task? So basically, my concern is not just minimizing loss on these particular data points, but rather I want to minimize the expected loss over the population in hand. So basically, this can achieve by another sort of data set, which we call it as a test data, which are drawn the same as the train set from the population, but they are independent from each other. And the test data is not the data that we use for training the model, but rather to estimate or to evaluate the model and to estimate the expected error for the model, to evaluate how much the model performs good in my task. So basically, the task is to assume some structure in the data set which are common between trained data and the test data. So let me explain you how I set up this experiment and what is this plot. Let's consider I have a plot which in x-axis, it shows the different dimensionality from a small dimension to the bigger dimension. The maximum one is 150. And on the y-axis, I have the test error for mean squared error, or MSE in short. I use two different models. One of them is k-nearest neighbor, or KNN. Another is linear regression to train and test. So let's discuss how I generated this dataset. Let's consider for a particular dimensionality D, I can generate uniformly generate the hypercube between -1 and 1. For the training data set, I can generate 1000 data point. So then by using some rule of true dependency, which is basically the linear combination of the features to generate or obtain the true Y for my problem. So for each of these feature data, I can generate a fixed random vector C, which can be multiplied by feature to get my target. So this C is constant over the experiment. And after having the training data set, I can train these two models. Then for obtaining the test data, I can generate the test data again with the same characteristic with this D dimension between -1 and 1, but it's independent from the training phase. And then I test the model and calculate the test MSE. As you can see, the orange line is the error for the linear regression model, and over the different dimensions, the error is rather constant and it's particularly low. But on the other hand, the test error for the KNN is a little worse than linear regression, but after we have more and more dimension, you can see the KNN performs much worse in comparison to linear regression. So this is basically the meaning of the curse of dimensionality. As the number of dimension grows, the data becomes more sparse, so KNN fails in this regard, which is really understandable. Let's consider we have two-dimensional data that we are going to generate between -and 1 for 1000 data points, and if you imagine these data points would be pretty close together, so they supposed to share a similar characteristic when they fall close to each other. But on the other hand, let's consider we have 150 dimension, and in this case, the solution space would be much more sparse, so two different independent data points will be much far from each other. So the assumption for KNN is similar objects supposed to have similar targets. It means those data points which are closer to each other supposed to have similar targets. And on the other hand, the assumption for linear regression says the targets are linear in features. It means the target is the linear combination of the feature, which is true because we created this rule and the data is generated in this way. So both assumptions here are correct, and one of them is more stronger than another one. The linear one is more stronger than KNN. So let's consider the same problem setup with the same models, with the same generated data, but the target is not the linear dependency between features, but rather calculating the norm of feature, calculating the absolute value. In this case, you can see still over the dimensions, linear model has a somehow constant MSE error, but it's more worse than the previous one because now the dependency are not linear anymore. But in the contrary, the KNN starts with a very small error close to zero for a low dimension, but still when we increase the dimension, the KNN performs worse in this regards. So still assumption for KNN is correct, but the linearity assumption is not valid anymore because the target is not the linear combination of the features anymore. So when we impose assumptions about the data, we are trying to restrict the space of possible solutions to get a best mapping, which supposed to minimize the expected loss over the whole population. So this restriction allows to overcome the curse of dimensionality, and on the other hand, wrong assumption led to wrong solutions. But how to check whether a model is good or not? Let's consider this plot, which we can see the model complexity or equivalent to the size of the solution space on the x-axis, and on the y-axis we have the prediction error. Let's consider we have a low complex model, but rather complex the solution space or data. In this case, both train and test error are rather high, and we call this situation as the underfitting. But on the contrary, on the right side of the plot, we can see the train error is very low, but the test error is very high. Of course, this is not a very real plot because the train and the test loss is not this much smooth, but rather with some fluctuation. But this is just a general illustration of the situation. So this situation would be overfitting. It means the model somehow learned all the data point in our training data, but it performs very bad on the test data. So what is our task? Our task is to find a sweet spot which the train and the test loss are rather close to each other before diverging for test loss to the very high value. So if we find this step, it means our model is very well fitted on the data. So the goal is to find the right level of the limitation to make a balance between being strict or not. As a summary, we talked about the supervised machine learning algorithm, which takes the dataset D, and we try to find a mapping which is supposed to estimate the true dependency of F, which is unknown. We talked about the different types of feature and their nature, and we talked about how can we encode them into numeric if we have categorical feature. And generally, the machine learning tries to solve optimization task by minimizing the loss function. And the choosing the right model is equivalent to applying the right assumption about the data. And also we use the test data to define if our model is overfitted or underfitted, and in general to understand how much our model works good in a general form. Thank you so much for watching the introduction to supervised learning.